let's get rolling. A linear system, so a linear system is something of the form ax equals b, that's a system of equations, is going to be called homogeneous if it can be written in the form ax equals 0. So in other words, we are selecting b to be the 0 vector. This turns out to be exceedingly important, as we will find out. Now, if you think back to our last lecture, we're really keenly interested in this equation and really how this equation has solutions. Now, for this particular value of b is 0, what we should notice is this equation is always consistent. Why is that? Because x equals 0 is always going to be a solution to that. And that is called the trivial solution. Any non-zero solution to this homogeneous equation is going to be called a non-trivial solution. All right, now, remember this theorem from 1.2. It was a rather lengthy one. It reads thus: a linear system is consistent if and only if the rightmost column is not a pivot column. Well, if you have a linear system, that turns into the augmented matrix A with 0. Is the last column, the rightmost column, ever going to be able to be a pivot column? Well, no, because it's always going to be comprised solely of zeros. So that means this is always consistent. Now, that means we're in this case. If the system is consistent, it has a unique solution in no free variables, or infinitely many solutions in at least one free variable. And so, what that means in terms of our equation here, ax equals 0, is we have a non-trivial solution. In other words, a solution that is not the 0 vector, if and only if we have a free variable. All right, what we want to do here is look at this linear system and ask ourselves, does it have a non-trivial solution? Okay, well, that is equivalent to us row reducing it and see if there's any free variables. So let's pop this into matrix form. What we'll do in our first step is use the first entry here to eliminate these two and multiply the top row by 1/3. So what we'll end up doing is E12 of 1, E13 of -2, and E1 of 1/3. This is the result. Now, I could do a lot more work here and go down the RREF, but I think the time has come where we use our brains a bit and just look at it. So I think it should be clear that this entry will turn this entry into a 0. Furthermore, I can easily make this entry a 1 and use it to eliminate this entry and make it a 0. So what we should see here is we basically have the form 1, some junk, 0, 1, junk, 0, 0, 0, and then the 0 vector over here. Now from this, we see that we have one free variable. Well, that means we have a non-trivial solution because we have a free variable by the last theorem. Now, how many degrees of freedom do we have? We only have 1 degree of freedom. Now, what that's going to mean for us is if we look at each of these equations, if we were to graph them, each of them would form a plane. Now, 3 planes can intersect in a multitude of ways. They can either not intersect at all, they could be completely parallel, they could have 2 intersecting and 1 not intersect, in which case that we would have a inconsistent system, or we could have the situation where we have all three of them intersecting in a line. It's like, it looks like that pinwheel I drew earlier. Oh gosh, this is going to be rough. There we go. They intersect in that line. Or we could have them all intersecting in a single point. Kind of like how the x, y, x, z, and y, z planes intersect. In this case, with 1 degree of freedom, that means we have them intersecting in a line. And if we were to graph this, we would see that that intersection is actually a line. All right, let's solve this homogeneous system and graphically interpret. Now this is all by assumption happening in R2. I could do this in R50, so we have a whole bunch of free variables, but let's use a little bit of common sense here. All right, so we have x1 minus 2x2. Well, that's 1, -2, 0. Well, if you look at that, that is already in reduced to echelon form. And I get x1 equals 2x2. Now you're probably thinking, my goodness, why did he do that step right there and then go to there when I could have just done that in one step? It's just a force of habit. So bear with me. Now x1 equals 2x2, we have 1 degree of freedom. And that means if we have 1 degree of freedom, what's this going to look like? Well, it's going to look like a line, isn't it? Now this line happens to pass through the origin. And if you think about it, this could be rewritten as how? X minus 2y equals 0. When you graph that, what do you get? Well, you get a line. All right, how about this one? This one, I'll skip this matrix conversion step and simply note that I get x1 equals -1/3 x2 plus 2x3. How many degrees of freedom do I have here? 2. So I can go in one direction, and I can go in another direction. 2 degrees of freedom span a plane. Now that's clear, because if I were to graph that, what would I get? I'd get a plane. All right. Now, in all those previous equations I was showing you, where we had to graphically interpret them, they were all of the form ax equals 0. In this one, I'm actually asking you to solve ax equals b. Let's do that. So I'll have 3, -3, 6, 5, -2, 1, -4, 4, -8, along with 7, -1, -4. If you're paying attention, you might notice something, but I'm not going to say anything quite yet. But hopefully you've noticed it. All right, this entry is going to be used to eliminate both of those by doing E12 of 1, and then E13 of -2, and then E1 of 1/3. Now in this next step, I'm going to use the second row to eliminate the third row, and at the same time multiply this row by 1/3. So in other words, what I'm going to do is E23 of 3 and E2 of 1/3. In this next step, I'm going to do E21 of -5/3. And upon finishing this step, my matrix will be in reduced row echelon form. So let's do that. As promised, there's my reduced row echelon form. What I want to do here is convert it back into a system. And what I'll have now is x, the vector, which is x, y, and z, equals my free part, that's some arbitrary constant alpha, plus the point part, -1, 2, 0. So what I want you to see here is this. The point part is that portion of the solution. This part right here, that's the free part of the solution. That's our degree of freedom. Now, if you think about this, I had 3 equations, 3 unknowns, so each one of those equations determined a plane. Now, what this is saying is the intersection of those 3 planes, well, it starts off at that particular point, -1, 2, 0, and it proceeds in that direction. So let's see if I can interject with the little slide after this that shows a graph for you so you can really get a better idea. Now, the next thing I really want to focus on is a little comment I made at the very beginning of the solution of this problem, namely, here I don't want to put that extra, there we go. Here I hinted that this should look familiar to you, namely that matrix there. We already solved that. Remember earlier on, we solved AX equals 0. That was a few slides back where I had you graphically interpret the solution. If you look at it, that graphical interpretation was right here. So what we've done is actually taken this particular equation, AX equals B, and notice that the solution can always be written in the particular form xp plus xn. Now, what do these stand for? Well, xp is always what you can always call your concrete solution. It's your particular solution. It's -1, 2, 0 in this case. xn is your infinitely many parts solution, you can almost think of it as. That comes from solving the homogeneous equation. So all the homogeneous solutions actually fall into that part of the actual total solution to this equation. So when we're looking at this particular equation and we're asking ourselves, will it have infinitely many solutions? Well, there's no point in actually solving AX equals B. We could simply solve AX equals 0, analyze the solution set to that equation, and then use it to determine if this has infinitely many solutions or not. That's a very interesting way of thinking about this. And here we go. Suppose AX equals B is consistent for some B with solution XP. Then the solution set to AX equals B is a set of all vectors of the form XP plus XN, where XN is any solution to AX equals 0. Let's make a little more sense of that. So we have AX. I'm claiming what? I'm claiming that X can be written as XP plus XN. So that's really A times XP plus XN. Well, what's that equal to? Well, that's AXP plus AX0, or XN rather, I'm sorry. Now, by hypothesis, AXP is a solution to AX equals B. So that means AXP must equal B. In AXN, XN is a solution to the homogeneous equation, therefore it must be 0. And so therefore we get AX equals the B we desire. All right, let's apply this. Do these two planes intersect? Well, to see if they intersect, that's equivalent to us simply taking their equations, converting them to an augmented matrix, like so, and then find the reduced or echelon form of that. Well, the reduced or echelon form of this is 1, 0, 3, 0, 0, 1, -2, 0. When I convert this back into a system, I'll get x equals -3z, y equals 2z, and z is free. So what's that mean for us? That means our solution is going to be of the form x is -3, 2, 1 times some arbitrary constant alpha. Now, because we're looking at the homogeneous situation here, this is going to be interpreted as a line through the origin in the direction of the vector -3, 2, 1. And you can think about that. So here are the three principal axes. What we have is, that's our, quote, y-intercept, if you think about this from the two-dimensional case. And we need to go -3, 2, 1. So there's my negative x-axis. Or actually, let's make this, what do I want to do? I want to do x, y, and z like that. So I go back -3, I go over 2, and then up 1. So there is my line. And if I were to graph these planes, which I'll do very sloppily, I'd have a plane going like this. And then I have another plane cutting it down through this, so that these two planes intersect along that particular line. And after this slide, I'll insert an actual pretty graph so you can see what's actually going on. As promised, here's a pretty graph. So if you look over here to the left, I have that plane, 2x minus y plus 8z equals 0. And this is the graph of it in the 3 space. If I add in this plane in red here, you see these two planes, they intersect in this line right here. Well, let me add the line in. And sure enough, there's the big old green line. This form I'm highlighting here in blue, -3t, 2t, and t, that's exactly what we got for our solution. We got the vector x, which is x, y, and z, equals -3, 2, 1 times some arbitrary constant t. So this is precisely what we should expect.